So in this example here, we're going to have the motion of a particle that's defined parametrically. So we have the motion of a particle modeled by the equations x equals 4 sine of t and y equals 2 cosine of t. And those are valid for any value where t is greater than or equal to 0. And there's 5 things that we want to do here. Actually more than 5 because some of them are multi-part. So we want to find vectors, acceleration, and velocity vectors. Let's start with that. How would I find the velocity vector? Derivative of what?
X and y.
Yeah, we're going to take the derivative of x and we'll take the derivative of y. What I might do here, I didn't ask you to do this, but I might find the position vector. The position vector is going to equal what?
4 sine t times 2 cosine t.
Yeah, it's just writing those two equations in component form. So the position vector would look like that. So then the velocity vector for part A, I'm going to write it v of t since it depends on t, is going to be the derivative of each of those components. What's the derivative of 4 sine of t? 4 cosine of t. And what's the derivative of 2 cosine of t? Negative 2 sine of t. And that right there, that's your velocity vector. Pretty easy, right? The acceleration vector, remember acceleration is the derivative of velocity. So the acceleration vector is going to be what? How do we find it? Yeah, take the derivative of these component-wise again, so they're independent of each other. So the derivative of 4 cosine of t is? Negative 4 sine of t. And the derivative of negative 2 sine of t? Negative 2 cosine of t. Okay, good. And that's part A. That's all you have to do. All right, so part B. We want to find the velocity, acceleration, speed, and direction at t equals pi over 4. So basically what I'm asking you to do here is just plug what we know into those equations that I just gave you. So for part B, let's start with the velocity at pi over 4. Is my answer for the velocity here, is that going to be a scalar, which is just a number, or is it going to be a vector? So the velocity here is going to be a vector because we need to know both components. We need to know the x component and the y component of the velocity. Otherwise, we'd be measuring speed. Okay, and we'll get there. We are going to measure the speed, but not yet. So this is going to be a vector, and all we have to do here is we have to plug in pi over 4 into this v of t here. When we do that, we're going to have 4 times the cosine of pi over 4. And we're going to have negative 2 times the sine of pi over 4. What is 4 cosine of pi over 4? What's cosine of pi over 4? Okay, 1 over the square root of 2. So it's going to be 4 over square root of 2. You guys agree with that? And then sine of pi over 4 is also 1 over square root of 2, right? So we're going to get negative 2 over the square root of 2. So my next question is, do you think we need to rationalize that? No, we don't. It's okay if you leave denominators with an irrational number. So that's okay. That would be an acceptable answer there. How about the acceleration? For acceleration, all we have to do, again, is plug in pi over 4. So the acceleration when t equals pi over 4, it's going to equal negative 4 times the sine and so what is negative 4 times the sine of pi over 4? Negative 4 over the square root of 2. And what is negative 2 times the cosine of pi over 4? Negative 2 over the square root of 2. And so this is my velocity vector, this is my acceleration vector. So I want to be clear about what these mean real quick. If I knew the position at this point, and I didn't ask you to find the position, but let's say I knew the position, I could plot the location of the point, but then I could also, in addition to that, draw a vector from that point to show how fast it's going and what direction it's going. And then I could also draw a vector from that point to show not only what direction it's going, which would be the velocity, but what direction the velocity is moving toward. So which way it's being pulled. Okay, so this acceleration vector, the acceleration would be in the direction of some force that's pulling on it. And so those of you that have taken physics, you guys just took a gravity test, right? This acceleration might be due to gravity, and so this would be the direction of the gravity here. So this, if we did this right, this vector right here would be pointing at the at the mass that's pulling on it. Actually, we want to find the speed here. To find the speed, I'm just going to label it as this, the magnitude of v. And how do we find the magnitude of v? Yeah, we're gonna use this right here, right? So we're gonna use this vector here and basically find the length of that vector by using the distance formula. So it's going to be the square root of the x component squared, so 4 over square root of 2 squared. I'm not going to skip steps here so that you can follow what we're doing here. Plus the y component, or the vertical component, squared. And so here we get 16 over 2, which is 8. Here we get 4 over 2, which is 2. And what's 8 plus 2? How do we find the direction? We actually don't have to find the angle. If you remember, we want to find the direction is going to be a vector. So we don't need to find the angle. If I did want you to find the angle, I would say find the direction angle. In this case, if I just ask you to find the direction, you can write it as a vector. And so the direction is going to be the velocity vector divided by what? Yeah, the magnitude of the velocity vector. So we're going to take the velocity vector, which is 4 over the square root of 2, comma, negative 2 over the square root of 2, and divide that by the magnitude of the velocity vector, which is our speed. And how do you think we're going to do that? To divide a vector by a scalar, you just take each component and divide it by the scalar. So it would be 4 over the square root of 2 divided by the square root of 10. So that's going to give us what? 4 over the square root of 20. And then over here we're going to have negative 2 over the square root of 20. Now I don't like those square root of 20s there. We should be able to simplify that. Square root of 20 is 2 square root of 5, right? So this is going to equal 2 over the square root of 5 and negative 1 over the square root of 5. Yeah? Okay, just for a quick aside exercise here, I want you to find the length of the direction vector. Do it real quick on your paper. Find the length or the magnitude of the direction vector. So the magnitude of the direction vector in this case is 1. The magnitude of the direction vector, if you do it right, is always going to be 1. So one thing to understand about the direction vector and the velocity vector is the velocity vector and the direction vector go in the same direction. So the velocity vector, if I were to graph that, would look something like maybe this. And the direction vector would look maybe something like this. And the thing to know is They go in the same direction, but the direction vector we only want it to tell us a direction and not how fast it's going in that direction. So what we do is we scale it down to 1, or a magnitude of 1. So when we divide by the speed, when we divide the velocity by the speed, we end up getting a magnitude of 1, and so all it tells us now is the direction. So the direction vector should always have a magnitude of 1. Part C is asking us to sketch it, so I'm going to kind of visualize what's going on here. My x component here is going to start at what? If t is 0, what's it going to start at? It's going to start at 0, and then it's going to go up, and it's going to go up to 4, and then it's going to go down to -4, and then up to 4, and down to -4, and it's going to go back and forth, right? So along the x-axis, we're going back and forth. Starting at 0, we're going up to 4, and down to -4, up to 4, down to -4, and so on. On the y-axis, we're going to start at what? 2, and we're going to go from 2 down to -2, up to +2, and down to -2, and so on, right? So if I just use what I know about the sine and the cosine, I know that the y-coordinate's going to start at 0, and the x-coordinate's going to start at 0, the y-coordinate's going to start at 2, so it's going to start at a point here on the y-axis. And I know that the x-coordinate's going to go up while the y-coordinate goes down, and it's going to, both of them are going to oscillate, and it's just going to go around like this. Does that seem to kind of make sense? So what kind of shape do you think we're getting out of this? It is going to be an ellipse. We could confirm that algebraically without a calculator if we wanted to by just plotting some points that we know, plugging in things like pi over 2, pi over 4, pi, 3 pi over 2, if we wanted to. Go ahead and type this into your calculator real quick. I want you to graph it, and I want you to note particularly where the intercepts are. We end up with an ellipse, and we know a little bit about ellipses. We could convert this to rectangular coordinates, rectangular graph if we want. We could do that using some of the tricks we talked about before with parametric equations. I'm not going to make you do that. But we would get a rectangular relation that would give us the same ellipse. Okay, so then we were asked to sketch the path of the particle. We've got that. And draw the velocity vector at the point 4, 0. So at this point here at 4, 0, we want to draw the velocity vector. How do we figure out what the velocity vector is going to be there? We have to put in the same t for x and y. So I need to figure out at what time the particle is going to be at this point.
Use the things and then solve for t.
Yeah, so we'll use our position vector and solve for t. So at the point 4, 0, ideally if we solve for t for one of them, we should get the same one for the other one. Otherwise something's going wrong here and our graph is wrong. So I'm going to pick this one here. When is cosine going to equal 0? Actually, that's a bad choice because cosine equals 0 at two different places on the interval. Let's go with this one. When does 4 sine of t equal 4? Or when does sine of t equal 1? At pi over 2. So what we're looking at here for part C is when t equals pi over 2. So when t equals pi over 2, what's the velocity vector going to be at pi over 2? So we put pi over 2 into our velocity vector. What's the cosine of pi over 2? 0. So our x component is going to be 0. And what is the sine of pi over 2? 1. So -2 times that is going to be -2. So our velocity vector is going to be 0, -2. So should I graph that right here like this? Would it make sense to graph it right there? No, where should I graph it?
The tail at the 4.
Yeah, put the tail at the point and go down 2. So the velocity of this particle at that point is going to be going down, straight down in that direction. Does that make sense? So part D asks if the particle is moving clockwise or counterclockwise. Clockwise or counterclockwise? Why?
Because the velocity is going down.
Yeah. So we just figured out that the velocity vector right here, that the particle's going down. So that means the particle's moving in this direction. So we know it's going clockwise. That's a pretty straightforward one if we know the velocity vector. And we know which direction clockwise and counterclockwise are. All right, and then the last one, part E. We want to find the distance traveled by the particle in one orbit. So first of all, on what interval is going to be one orbit? That was awkwardly worded, but yeah. So it's going to be from 0 to 2 pi. That'll give us one orbit, and we get that just by knowing about the trig functions. And so to find the distance traveled, what are we going to do?
Distance or arc length formula.
Yeah, it's the arc length formula. So it's going to be the integral from 0 to 2 pi of the square root of dx dt squared, which we know the velocity. So it's basically the magnitude of the velocity function, or the velocity vector. So it's going to be 4 cosine of t squared plus -2 sine of t squared with respect to t. That one, I would expect you to just use a calculator. We don't really have the tools right now to evaluate that. It's not going to be a perfect square, so we can't take the square root of it. So you can plug that into your calculator. We're getting an answer about 19.377. So the length of the orbit, or the distance traveled by the particle in one orbit, is going to be about 19.377 units.